Okay, so welcome back. Today we will do a few things. We will do a number of theorems. Again, everything is something that you have already seen, so maybe a bit quick. But as I said, Rodin's proof may be slightly different from whatever you have seen, so that's a good thing to go through it quickly. You would have seen certain proofs before, and you will see another slightly different approach. Okay, so what did we do last time? Can someone quickly tell me? We'll come to the slides, but before that, let's talk a little bit. And last Friday, what did we do?
We looked at isolated singularities at the end and categorized them into three.
And before the break?
Before the break,
I'm also thinking with you. Before the break, we did this one. Zero.
it's an integral domain. Yeah.
Yeah. That was a corollary to
identity theorem.
And identity theorem, the main point was that if you have a holomorphic function on a region, I think connectedness played a crucial role in the proof on a region. Then we showed that it has its set of zeros has no limit point, right? As a corollary, we proved the identity theorem, and as a corollary, all of you did in the break a proof that holomorphic functions on a region, it's an integral domain. In fact, we saw two different proofs. One proof I started and others finished using continuity of one of those, and then Ariman gave this other proof, which made use of, if I remember correctly, the zeros are countable, right? Ariman, that was the argument, no?
Yeah.
Yeah, good. Okay, so that's what we did before the break, and then after the break, we did isolated singularities, and then some of us had slightly longish WhatsApp discussion on the definition of an isolated singularity. So as I also said on WhatsApp, either one is okay. So some books, you know, they are very careful that it is first of all a singularity and then it's isolated. If you feel comfortable with that, take that. We don't need to worry so much about it. FS analytic in a deleted neighborhood is fine for us. In which case, removable singularities we will not bother so much. So the real isolated singularities are pole and essential singularities. So it will not affect anything. So either one you can take. Let's stick to Rodin. Yeah. So I will not assert that it's a singularity to start with. It doesn't matter. Okay, so let's go to the slides then. Let me start sharing the screen. Just confirm you can see my file. The file is visible, no? The beamer, the presentation is visible, right? Can one of you confirm?
I can't see it so far. Yeah, now it's visible.
Now it has come. Okay, good. So it's a bit slow. I hope Wi-Fi is okay. Okay, it's visible now. So lecture 5. So what we are going to cover today, you can see a number of names. So let's see what they are. Liouville, of course, is the famous Liouville's theorem. I have taught this course before. I have learned this long back, but still, when I type Liouville, I have to check the spelling once again. So, yeah, I guess this is correct. What is MMT? Quickly, can someone give me the full form?
Maximum modulus theorem.
Or the minimum modulus theorem. So, maximum modulus theorem. As a corollary, the minimum modulus will follow. FTA?
Fundamental theorem of algebra.
Then we will have Cauchy's estimates, and then what is called compact convergence. I don't know whether you know the word compact convergence, but this is something that you already know. What this means is uniform convergence on compact subsets. So some people call it compact convergence. Okay, so these are the things that we will do today. So there's a result on compact convergence. Holomorphic functions. When we study holomorphic functions, this is the convergence that is most natural and most useful. So the last result of today's lecture will be something on that, which basically says if you have holomorphic functions on a domain Fn, and if Fn converges to F uniformly on compact subsets, then F is also holomorphic. Not just that, the derivative of Fn prime will converge uniformly on compact subsets to the derivative of F prime. Second derivative will converge to second derivative. So it's a very beautiful situation. Okay, so that's the very last slide. So let's come to it one by one. So as you can see, we are covering a lot of names, but it won't take all that much time. Okay. Anyway, it will be a quick recap only because you have seen these things already once. Okay, so very quickly, last lectures. Yeah, I can't stress the importance of the identity theorem. So let me recall that once again. Last lecture we saw the identity theorem. The key was zeros are isolated. So I'm abbreviating it now, ZAI. Zeros are isolated. So how was this proved? We considered zero set of f denoted by z of f, and we considered the set of limit points of z of f in omega, where omega is your region. Region was important, connectedness was important. Okay, which is a region, and this set of limit points A, we are going to show that it's both closed and open. Closed is obvious because it's set of limit points of a certain set, so it's automatically closed. So this part is obvious, closed is obvious, and open needed a little bit of work. And what was the main idea? F is holomorphic, so you given a disk, you can expand it as a power series. So given a disk DAR, you can expand it as a power series. And then if you remember, we are looking at the coefficients and there are of the power series, and there are two cases. Either all the coefficients are zero or not all coefficients are zero. If all the coefficients are zero, then F is identically zero on DAR. F is identically zero on DAR, which means DAR is contained in ZF, and in fact DAR is contained in this set A, because in an open set every point is a limit point. So DAR is contained in A, which would say that A is an interior point of A. Otherwise, if F is not identically zero, you can write F of Z equal to Z minus A power M times GZ, with G a holomorphic function. Right, you have the power series expansion of F, and then you pick the smallest m such that Cm is non-zero and use that in order to get like this, where Gz is holomorphic and Ga is not equal to 0 because m is the order of A, and because G is holomorphic, therefore G is continuous, therefore there's a neighborhood of A in which G is not 0, which means that F has no other 0 in that neighborhood, which means A is isolated. So this is if F is not identically 0 on DAR. Otherwise, A was an interior point. So now if you take A in A is a limit point of ZF. Because it's a limit point, it cannot be an interior point. And therefore, from this argument, it follows that A is an isolated point. So A is also open. So A is both closed and open. So the options are A is either the whole set omega or A is the empty set. A is the whole set omega, meaning F is identically 0. So if F is not identically 0, then A is empty set, which is what we wanted to show. Set of limit points is empty. Zeros are isolated. Okay, then we had a break, and then after the break we discussed isolated singularities. A point is an isolated singularity if there is a small deleted neighborhood on which f is holomorphic. So an isolated singularity for a function f is a point A in a small deleted neighborhood of which f is given to be f is holomorphic. And then we classified them. They are removable or pole or essential. Removable meaning you can redefine so that it's holomorphic throughout the disk. It was holomorphic in a deleted neighborhood, and you can redefine so that it's holomorphic throughout, then it's removable. A pole we defined in terms of you can take a principal part and subtract, you can construct a principal part and subtract, and then it will have a removable singularity at A. So that was pole, and essential was not removable and not pole. And removable, you remember, we had a boundedness result, right? If a point is a removable singularity, if and only if in the deleted neighborhood, in a deleted neighborhood of that point, f is bounded. And this is what is called, maybe I didn't say the name last time, but you would have seen in your last course, it is called RRST. What is RRST? What's the full form?
Riemann's removable.
Yeah.
Riemann's removable singularity
Theorem. RRST, Riemann removable singularity theorem. So that's what we stated and proved. And then we defined a pole. Our definition was that you can construct a principal part and subtract it out so that you get holomorphicity, meaning removable singularity at that point. And then on WhatsApp, many of you checked already. Otherwise, also it's not difficult to check that a pole is same as saying limit z going to a of f of z is infinity, which is same as saying limit z going to a of mod of f of z is infinity. And if it's neither removable nor pole, then we actually proved this will be the definition of essential, and then we actually proved something. So essential we could have defined as neither removable nor pole, right? But then we also proved a statement, a certain density statement. What was that? It was that you can take any disk around A and you can take its image under F, and that is dense in C. So f of DAR for any R is dense in C. Okay, so given any complex number arbitrarily close to the essential singularity, you have a sequence of points such that the images of those points converges to that given point from C. So this we proved. In fact, we proved the contrapositive. We proved that if this is not true, then the point A has to be either removable or a pole. This is what we proved. Satisfies the density property, and this also has a name. It is called the Casorati-Weierstrass theorem. So it says that essential singularity has this property that images of the deleted neighborhood any deleted neighborhood around an essential singularity, if you take the image, that is dense in the whole of C. Okay. In the break, if you want, we can talk about these notions once again. It's up to you. If someone thinks there's a little bit of confusion or not fully clear from last lecture, feel free to ask me. Also remember to ask me about the big Picard theorem, which is what we will prove at the very end of this course. So it can be motivated using this Casorati-Weierstrass theorem. So let's get to that at that time. In the break, you can ask me. Okay, so today we will do Liouville's theorem, MMT, which is maximum modulus theorem, as an immediate corollary, minimum modulus theorem, then FTA, which is the fundamental theorem of algebra. C is algebraically closed, Cauchy's estimates, which you would have seen, which we will recall, and compact convergence, also known as uniform convergence on compact sets. Okay, so that is what is there for us to do today. So let's start. So let's start by a little bit of trigonometric preparation. Okay, and then so this is Rudin's approach, and then all these theorems are going to fall very easily from an identity which we are going to show. So basically this identity is on, so you're going to consider continuous functions on a compact interval, say minus pi to pi, and you are going to put an inner product on that thing, right? On function spaces, there's a very natural inner product that you can put, which is that the inner product of f and g is integral of fx gx bar dx. Fx gx bar dx. You can normalize appropriately if you want. So it's an inner product. It's an inner product space, and so we are going to make use of what is called Parsifal's identity for inner product spaces and get a nice identity out of this. So let's see that. Yeah. So suppose f has a power series expansion on DAR. Suppose this is given, and then the claim is you have this identity. So left hand side is an infinite sum using the coefficients of the power series. And the small r is any small r which is less than the capital R on which the power series is given. So you have that infinite sum on the left hand side, and what is the right hand side? Right hand side is this inner product that I mentioned. I said that given two functions f and g, you can define an inner product as integral of fx gx bar. So in particular, inner product of f comma f will be integral of fx bar, which is mod fx square. So this is certain inner product with itself. Okay, what is the inner product here? I have normalized it as 1 by 2 pi integral minus pi to pi f of a plus r e power I theta times g of a plus r e power I theta bar d theta. Under that inner product, this is just the inner product of f with itself. Okay, so this is the claim. And why is that? So proof is quick. So first note that f of a plus r e power I theta. What is it? So this is the formula for f, this power series expansion. So you plug in z equal to a plus r e power I theta. What will you get here? Z minus a will be r e power I theta and power n. So it will be r power n e power I n theta. So Cn r power n e power I n theta. This you will get, and because r is less than r, right? So this is given, so which means the radius of convergence of this power series is bigger than capital R. So inside that circle of inside on the disk of convergence, you have uniform convergence. So if you take this one, because R is less than capital R, which is less than radius of convergence, you have this sum to be uniformly convergent, and this is uniformly convergent wherever. So you let us take it on minus pi to pi. As theta varies on minus pi to pi, you have uniform convergence because it's coming from a power series on a disk of convergence. So this you have, and now what we are going to do is I am going to check what is integral of f of a plus r e power I theta if you integrate against e power minus I n theta. Okay, so f of a plus r e power I theta, if you integrate with respect to e power minus I n theta, you have this formula for f of a plus r e power I theta. You multiply by e power minus I n theta and integrate. So can you see that easily? You are integrating this after multiplying by, let us say, e power minus I m theta, m, let us say. So this will be integral of sum this times e power minus I m theta. So that is e power I times n minus m theta. Integral of the sum is sum of the integrals because of uniform convergence. So you just have to do integral of Cn r power n e power I n minus m theta d theta. So Cn and r power n comes out. So integral of e power I times n minus m theta d theta, you can easily check. It is non-zero precisely when n equal to m. Otherwise it is 0. So only one term will remain, and that will be n equal to m term. So when you do this, what you will get is you will get Cn r power n, and because of 1 by 2 pi normalization, that integral will be 1. So when you integrate with respect to e power minus I n theta, only Cn r power n will remain. All other terms will be 0, and this is true for every n. Okay. So this is easy. It's just changing integral of the sum as sum of integrals, nothing more. Okay. Now Parsifal's identity is the following. If you have an inner product space, you have seen this. So this is a vast generalization of Pythagoras theorem. On an inner product space, if you have vector x, then norm of x square is summation of modulus of inner product of xv square, where is v from? V is from an orthonormal basis. So what is orthonormal basis? They are mutually orthogonal and each one has norm 1 with respect to this inner product. Norm 1. Okay, so orthonormal basis, and there is also this condition required in order to prove this generally, which is that the linear span of this basis is dense. Linear span of this basis is dense. So it's well known that, or either you have seen or you might see in some other course, but let's take it for granted that trigonometric functions have this property. E power I n theta. Trigonometric functions meaning in complex notation it's e power I n theta, right? Cos n theta plus I n sin theta. So if you take linear span of e power, so finite linear combinations of e power I n theta, then they are dense in the space of continuous functions. Maybe you have seen this already. Any continuous functions can be approximated by linear combinations of e power I n theta. So this property is true for us. So you can apply the Parsifal's identity. So what will you get? What is left? Left is norm x square. So x I am taking as this function f of a plus r e power I theta. So norm x square is nothing but this one, 1 by 2 pi integral minus pi to pi f of a plus r e power I theta times its bar, so that is modulus of that square d theta. So that is norm x square, which is summation over. So what are the what is the basis for this space? E power I n theta will form an orthonormal basis. So for a given e power I n theta, which is a particular v, you are taking inner product with x comma v, which is this, which is Cn r power n. So you are taking modulus square, so you got mod Cn square r power 2n and summation over the basis as n varies. So n going from 0 to infinity. So basically this is Parsifal's identity, and this proves the identity that we want. Okay, so this is the identity that we wanted to prove, and that is true. And this almost all these results we are going to make use of this identity and prove quite easily. So let's start with Liouville. Okay, so remember this identity. If f has a power series expansion on a disk given as summation Cn z minus a power n, then for any r which is less than the radius of convergence, you have this identity. For any r less than the radius of convergence, you have this identity 1 by 2 pi integral minus pi to pi modulus of f of a plus r e power I theta square d theta is summation mod Cn square r power 2n. So you're going to get a good grasp on the coefficients of a power series expansion using this. You can see this, right? In all these theorems, either f is bounded or something about f is given, and that you can plug in here and you can conclude something about the coefficients via this identity. This is the trick that we are going to use in all these results. So let's start with Liouville. So what is Liouville? Entire and bounded is constant. So suppose f is entire, then modulus, then f of z is summation c and z power n, and this is true for all z and c, right? Because it is entire. So radius of convergence of this power series is infinity. So the same power series works throughout Z. And suppose it is also bounded. So mod Fz is less than some m. There exists m for all Z and C, entire and bounded. Then we will use our identity. So summation mod Cn square r power 2n, summation mod Cn square r power 2n is equal to, our identity is this, right? And now modulus of this is strictly less than m. So this is less than m square. That comes out, and integral d theta is 2 pi. That cancels with this 2 pi. So this is less than m square. So you're getting from our assumptions, you are getting that this power, this summation, this infinite sum is less than m square. So what does that mean? This is true for all r, right? This is true for all r, and this is true for all r because it is entire. So for any r less than infinity, this identity is true. So you're getting this to be less than m square for all r. But is that possible? As r goes, if cn's are non-zero, as r increases, this will go outside m square, so you cannot bound this. So the only possibility is that all these cn's are 0 except for r equal to, except for n equal to 0. If r is not coming there, that c0 will remain. If r is coming, then c1 onwards, all those coefficients have to be 0. That's the only way out. So cn is 0 for all n bigger than or equal to 1, which means f of z is just c0. So f is identically equal to c0 and it's constant. So this Lewis theorem. Okay, so that was quick. And now let's show MMT, maximum modulus theorem. So what do we need to show? We need to show that if f is holomorphic on a region, for MMT also, I stress that it is a region. Connectedness is important, and we need to show that if f is in h omega, where omega is a region, then I want to say, so it is maximum modulus theorem. The modulus of f cannot attain its maximum, cannot attain a maximum value. Right, so this is maximum modulus theorem, and similarly minimum modulus theorem, the modulus of f cannot attain a minimum. There's one more condition that you have to add for minimum modulus theorem, that it is not 0 throughout. It has no 0. Then minimum cannot be attained. Otherwise, of course, 0 is a minimum for the modulus. Okay, so let's prove maximum modulus theorem. We have to show that f has no local maximum at any point in omega. What is local maximum? A disk on which you are a small disk on which you are attaining a maximum. So you want to show that there's no local maximum at any point in omega. This is maximum modulus theorem, unless of course f is a constant. So this is what we need to show. So take a disk, closed disk. So when I put bar, that means mod z is less than or equal to r, less than or equal to the closed disk. So you take a closed disk contained in omega, and you're going to claim that modulus of fa is strictly less than maximum of f of modulus of f of a plus r e power I theta. Assume f is not a constant, and then you are going to claim this. So this is what we are going to claim. So suppose not. If this is not true, then what will happen? If this is not true, if mod f of a is not strictly less than the maximum value of the modulus on the boundary of this circle, boundary of this disk, on the boundary circle, you take the maximum value on the boundary circle, and we are going to claim that the value at the center is strictly less than this. If this is not true, then modulus of f of a is bigger than or equal to modulus of f of a plus r e power I theta for all theta, right? You're contradicting this one. So modulus of f of a is bigger than or equal to this value, maximum of this, which means for all theta it's bigger than or equal to this. Again, we will apply our identity. So you consider summation mod cn square r power 2n. Remember, it is this integral. And you have modulus of f of a plus r e power I theta is less than or equal to, I'm missing a modulus line here, so I'll correct it later. Greater than or equal to, this is less than or equal to modulus of f of a. So you can plug in here. So you'll get mod fa square d theta. Integral d theta is 2 pi, which gets cancelled. So this is less than or equal to mod fa square. Okay, so this is what you will get. You are getting this is less than or equal to mod fa square. And what is the conclusion? And what is f of a? F of a is F of A is, so yeah, so you're doing this after expanding it as a power series. I haven't written it here, but if as a power series expansion only, you have this identity. So on this disk, given this disk, you have a power series expansion. So I haven't written all the details here. So assume that F has a power series expansion summation Cn z minus a power n, and then you have this identity. And then what is mod Fa? Fa is C naught. So this is equal to mod C naught square. What can you conclude from this? You are saying that this is summation mod Cn square r power 2n is less than or equal to mod C naught square. So from this you can conclude that Cn is 0 for all n bigger than or equal to 1, right? Because in this it is mod C naught square plus other terms. So if one of the Ci is non-zero, you are adding something to it, right? R is some positive number. So if one of the Ci is non-zero, then you are adding something to mod Z naught square. So this cannot be true. So from this you conclude that Cn is 0 for all n bigger than or equal to 1. But if this is true, then what is F? F of Z is summation Cn z minus a power n. And all the Cn's are 0 when n is bigger than or equal to 1. So f of z is nothing but C naught, but C naught is f of a. So you have concluded that f of z equal to f of a. Where have you concluded this? On the disk where you have the power series expansion, which is DAR. So you have concluded f of z equal to f of a on DAR. In the disk DAR, you have concluded this. From this Cn is 0 for all n greater than or equal to 1. Therefore, I am claiming that f of z equal to f of a throughout omega. So what we have concluded using this identity is f of z equal to f of a in this disk DAR. And therefore, I am claiming that this identity is true, f of z equal to f of a throughout the disk. Why is that? Can someone tell me?
The open disk has limit points and an
Open
identity
is
theorem.
point, and therefore you can apply the identity theorem. So on a set which has a limit point, if two functions agree, then they agree everywhere. So this shows that f is a constant on omega, and this is what we had to show, right? We want to show that f has no local maximum. If f had if f had a local maximum, in particular, you get this identity, right? If f has a local maximum, that meaning on a disk, uh, if there is a point inside the disk, right, maximum is attained only on the boundary is what you have to say. On an open disk, there is no local maximum. On an open disk, there is no maximum. Or on a another way of saying is on a closed disk, maximum is attained only on the boundary. So if there is a point inside where the maximum is attained, you are showing that the function is constant throughout. So you have proved MMT. And this is the minimum modulus theorem. If mod Fa is bigger than, strictly bigger than the minimum of, so you want to say that the minimum is also attained only on the boundary. There's no local minimum. If this is true, mod Fa is strictly bigger than minimum of mod f of a plus r e power I theta, if f has no 0 in DAR. So how will you prove this? So this result is called minimum modulus theorem, and the proof is that so you have to assume that f has no 0, right? Because if f has a 0, then modulus, of course, the minimum is 0. 0 minimum is attained. So if f has no 0 locally on that disk, then you want to say that no minimum is attained inside. Minimum can be only on the boundary, or it's an open disk, then there is no local minimum. So if f attains 0 on the boundary, then of course this is true, right? If this is 0 for some theta, if this is 0, then of course this is true, so there's nothing to prove. Otherwise, on the closed disk DAR, f has no 0. So what you can do is you can take a region containing this closed disk, and where f has no 0 on that region, And now you consider the function 1 by f. Because f has no 0, 1 by f is holomorphic, it's well defined and holomorphic. And apply the maximum modulus theorem to 1 by f and conclude the minimum modulus theorem for f. So proof of minimum modulus theorem is apply the maximum modulus theorem for the function 1 by f. But the function 1 by f has to be well defined, meaning f should not vanish, and therefore you have to put this condition in the theorem, in the statement of the theorem itself. So this is the minimum modulus theorem. Now, fundamental theorem of algebra, I think you might have seen in 412. So this has many wonderful proofs. Whatever course you have, I think you may have a proof of fundamental theorem of algebra. In Galois theory, you will have one proof. In algebraic topology, you will see another proof. In complex analysis, in 412, you would have seen one proof. Most likely, you would have proved it as a corollary to Lewis theorem. So what would be that proof? What would be the structure of that proof? Take a polynomial. You want to say that it has, if it is not constant, you want to say that it has at least one zero. And by induction, you can factorize it linearly as a product of linear polynomials. Right? So basically, you want to show that it has at least one zero. C is algebraically closed. It has at least one zero. So suppose not, p has no zero, then of course you will argue with 1 by p, and 1 by p will be an entire function because p is entire and p has no zero, you are assuming, therefore 1 by p will be entire, and you will argue in two different ways and show that 1 by p is bounded. Right? This is how you would have done it. Most likely this is what you would have done. So how will you show that 1 by p is bounded? You first of all will notice that uh, limit of this function 1 by p as z going to infinity is 0, and therefore beyond a stage, if mod z is bigger than some, there is an m, such that if mod z is bigger than m, then of course 1 by p is bounded. And mod z less than or equal to m, 1 by p is anyway bounded because of extreme value theorem. On a compact set, a continuous function takes its extreme values. And therefore you get boundedness throughout, and it's a bounded entire function, and therefore it has to be a constant by Lewis theorem. Here is a slightly different proof. We are not using Liouville, we are using MMT. Okay. So you take pz equal to this polynomial, and the claim is that so choose an r big enough so that for all theta between 0 and 2 pi, p of r e power I theta, p of r e power I theta, its modulus is strictly bigger than p of 0. So choose an r. So you have to think for a minute. You have to think a little bit to convince yourself that such an r exists. Now let me give it as an assignment. So Rudin says that in fact you can choose r bigger than this particular quantity in terms of the coefficients of the polynomial, and then this property is true. So if you choose r bigger than this, then modulus of p of r e power I theta is bigger than p of 0. So you might have already got a mail in your LDAP ID. Using Google Forms, I have created an assignment and I have invited all of you to submit the assignment. There are two questions. This is question number 1. And question number 2 will come towards the end of the slides. And these two are assignments, each carrying 5 marks. I will continue to give many such assignments, and the evaluation will be done in two ways. One, in the Google form itself, you have to, I have given a paragraph space. So you can type your answer. So be precise, you cannot write a whole essay there. The space is limited. So first you try out your argument on a piece of paper and then take the important points, and in the Google form you fill it, submit. Okay, so this assignment is due by tomorrow noon. By tomorrow 12 o'clock you should submit this assignment. There's one more question. And so if I'm completely convinced about your answer, I will give some marks. But not just that, assignment has 2 parts. And if I feel like questioning you on the Friday class or some other class, I will ask you how you got that answer, etc. I will ask you in our break. So assignment will have these two parts. First, you have to submit your answer. I will look at your answer and then I will interview you on your answer, how you got it. So I want to make sure that you have completely understood your answer. Okay, so this is the first one. So do it. Assume this is done. Now assume P has no zeros. You want to show that P has at least one zero. If P has no zero, take F equal to 1 by P. And because of this condition, what will be the condition on F? Mod of F of 0 will be strictly bigger than mod of F of R e power I theta. But this is not possible by MMT. In fact, in MMT you have seen, in the proof of MMT you have seen that you had this identity. Modulus of f of a is strictly less than maximum over theta modulus of f of a plus r e power I theta. Right? Therefore, f of 0 cannot be strictly bigger than modulus of f of r e power I theta. This cannot happen. So that's a contradiction, and that's because P has no zero. So this is a slightly different proof of a fundamental theorem of algebra. Your earlier proof most likely used Liouville's theorem straight away. It's a slight variant, and this part is the assignment which you should submit by. I will be very strict about the deadline, and you should not email me, etc. It should be in the Google form so that everything is recorded correctly. So I'll be strict about the deadline tomorrow, 12 o'clock. 12 noon. Okay, tomorrow lunchtime, 12 o'clock. So let's take a break and discuss a little bit and come back and we will do Cauchy's estimates. So what is remaining? Today's agenda was Liouville's theorem. Maximum modulus theorem, minimum modulus theorem, and fundamental theorem of algebra. This much is done, and remaining Cauchy's estimates and compact convergence. We want to show that if Fn converges to F uniformly on compact subsets on a domain omega, and if Fn's are holomorphic, then F is also holomorphic. Not just that, Fn prime and F prime will be holomorphic, and Fn prime converges to F prime uniformly on compact sets, and you can repeat this process, and the kth derivative of Fn will converge uniformly on compact sets to kth derivative of F. So it's a very beautiful, satisfying result. So these two things will come back after the break. Let's stop here. Stop this recording.